Welcome along to the Coaching Corner. It's good to see some new faces from all around the world today. I'd like to acknowledge the sponsorship of Philips, who kindly support us in this monthly endeavour for the Coaching Corner. Tonight we have a guest speaker. We have Ashley Barker from ProbeLogic, who's going to, I'm going to get all ultrasound nerdy, but we're going to look at the insides of probes and take a look at what happens when you don't look after them well. I do want to just mention up front that if anyone has any questions, this Coaching Corner is being recorded and others do view it at a later date. But if you have questions that you don't want to be on air and recorded, please just hang on at the end and we can talk you through those. And if you have any clinical questions that you would like to suggest a topic for next month's Coaching Corner, feel free to get in touch with me. My contact details are up on the screen here. And so without further ado, I am going to throw and introduce you to Ashley, who, like I said, from ProbeLogic, and he's going to take us on a tour of his lab. And I've had a sneak peek already and it's pretty wicked. So over to you, Ashley.
Excellent. You able to hear me still?
Yes, great.
Perfect. That's great. So I'll give a quick introduction first. As Sue-Ann said, my name is Ashley. I'm from a company called ProbeLogic, and we specialize in repairing transducers. So I think when it comes to transducer damage, we've seen every possible thing. I've probably the one that stands out the most as an unusual fault that I've seen is a probe came in and the cord was completely pulled apart in the middle. And I rang up the customer and said, what happened here? And they said, well, one half got in an elevator and the other half didn't. So we've seen everything. So what I'd like to do first is probably just show you a probe that is pulled apart. And we'll basically just run through the different components. And then we can talk about what breaks, because it's much easier if you know what all the parts are inside. And you have to excuse my cough. I've got a bit of man flu.
As long as it's not corona, we're good.
Yeah, that's right. All right, so I'm just going to flip my camera around. Right, have you still got me? You can see that?
We saw that.
Excellent. So this is a probe. It is an L12.5 Philips probe that we have pulled apart for the purpose of you guys being able to see what's inside. So you can see in the head of the probe up the top here, there's a whole bunch of circuitry. Some probes will have this circuitry, some won't. The reason that this one does is it's multiplexed. So when they say a probe is multiplexed, this is basically the components that are doing that. And basically what it allows them to do is run much more elements in the end down less wires. So the wires are being shared between elements. Otherwise you'd have, on a probe that has so many elements in the end, you'd have this big giant cable that would be very annoying. So if we look again at this, what we've actually done on the end here is you can see that gray surface, which is the lens that you normally see, silicon lens. Then there's that silver section off to the side. That's the matching layer. So we've just cut the gray section off and you can see that matching layer. And that matches the acoustic impedance of the crystals with the lens material. And then finally, that little tiny section up here is the actual array. So we've pulled that matching layer off. And I don't know if the phone is actually good enough that you can see the individual crystals there, but with your eye, you can actually see individual crystals. Right?
It's a little blurry, but you can get an impression.
You can sort of see it.
Yeah.
Okay. So then getting some of the terminology right, this section here is the strain relief, right? And its purpose is, as the cable gets pulled and bent, it allows the cable to bend over a larger radius rather than just bending on one spot where it will eventually break. Right. Then we've obviously got the cable comes down, and I've pulled apart the connector end as well so that you can actually have a look inside there. So obviously the front part of the connector that you're very used to. And then there's some circuitry, and some probes have more complicated circuitry than others, but most probes will have lots and lots of these little inductors. You can see those little blue inductors, and their purpose is again to match impedances, this time electrical impedance, not acoustic impedance, of the cables connecting up and going up to the crystals. It's all impedance matching. And so every element has one of those attached to it. Right, so that sort of gives you a bit of sort of a feel for things. So what I want to do now is just run through, I basically just went through some old probes we have and found some very familiar looking damage that I thought I can sort of run you guys through. So this one here, what is this? This is a Siemens probe. And you can see the needle damage on the lens there. So basically someone hasn't been careful when doing injections and they've basically stabbed the needle straight into the end of the probe. And that's okay if it just takes out the actual lens material, but and if it were to do that, you want to get it dealt with quickly, because if water gets into your array, it'll corrode the array. And so it's important to get it dealt with quickly, and you start getting lots of horribleness, and it's an infection control problem and all these sorts of things. But yeah, basically that's not what you want to do with needles. Moving to the next one, this is sort of a bit of a different sort of look of lens damage. This is on a...
Can you give us a bit of an idea of expense? Like, I know commercial in confidence, but like ballpark just for that needle damage to the surface of the probe, we're talking hundreds of dollars, thousands of dollars.
So again, it would be a little bit dependent on what damage has been done, because if that needle's cut right through the matching layer, then we need to replace the matching layer as well. But you'd be looking for something like that, probably the top figure, probably about 1850, something like that in Australian dollars.
But if it's not crystals out off the, if it's not crystals out, so you've got lines in the screen, that means it's gone deeper. That means it's more expensive. Would that be correct? If
it's actually damaged the crystals, then yeah, it's definitely going to be more expensive than that. And at that point, it may or may not be repairable. It depends whether an array is available for that particular probe.
Because sometimes you might be better off buying a second-hand probe than trying to repair the one that's already damaged. I suppose a bit like writing off a car in a way, isn't it?
Yeah, I mean, it is. Again, it's probe dependent, and it depends what damage is there. We're able to assess that, and we're also able to sort of, advise you on whether that's a sensible thing or not.
Yeah.
This one here is again lens damage, and let's see if I don't know if that's visible there. Are you guys able to see that?
Yeah.
So that one's a bit less obvious to see, but basically you can see that there's a little nick out of it, and that's really common. We see that all the time when we go through clinics, and we go through and do probe testing for people, and there's so many probes like that that people just haven't noticed. And it is an electrical safety hazard. I actually did a video a few years ago where I produced a fault in a machine and had the lens damaged on a probe. So it was a double fault, but yeah, basically it's possible to apply mains straight to the patient. So if your lens is damaged, you really want to get it fixed. A lot of the time, you'll start to see, particularly if you're using alcohol to clean your lenses, you can start to see like a crazing, and eventually the crazing turns to like micro cracks, almost like a dry riverbed type thing. And that's bad too. So you really must not use alcohol to clean probes. Moving on again, this one here, hockey stick probe, and whoops, someone's ripped the end off of the wraparound lens there. And yeah, they've done a fair bit of damage on that. But that's another common one. So they do break if you apply too much force. I'm not quite sure how they managed to do that, but it's
like the dogs chewed it.
yeah, or maybe they had rats in the clinic. Who knows? Yeah, that's just. I guess it's a case of just looking after your probes and really, really taking care with them, because they are breakable. Another really common thing we see moving down from the lenses is, hopefully you can see this, all the cracking that's happening there.
It's a bit better, a bit further away. Yeah, that's better.
Yeah, okay. So if you can see all that cracking that's occurring around there, and you get that on pretty much any brand of probe, if it's being dropped, it starts just cracking out the sides, and that is repairable, and definitely worth repairing, because again, if you get fluid in there, then it's going to get into all that electronics. And we've had probes in where we've popped the cases apart and there's just like a green, horrible sludge that pours out. It's disgusting. So yeah, if there's any form of hole, it's worth getting it plugged, basically. This one here might be harder to see, and you've probably even seen them in the past, but it's a bit hard to do one-handed. Alan, are you able to just give that a pull? I've got some assistance here.
Very good assistance.
Yeah. So this is just the cases start to separate.
And the back pulls off.
And the back pulls off there. But you can see those cases separating. That is super common. And again, worth dealing with because it's going to fill with sludge, particularly on probes that are used, you know, like transvaginal probes and things like that. You really don't want them full of nastiness. It's just not pleasant. This probe here, this is quite a common thing, and I've yet to figure out exactly what causes it, but across the whole of the world and across, you know, many clinics, cables turn yellow like this. And like I say, yet to find out what people are doing to actually cause that. It can be fixed, but it just looks nasty. So if anyone has any thoughts on that, I'd really love to know what they think might do it. Some clinics do it and some don't. So maybe it's to do with the cleaning solution or something like that.
It's not a getting hot sort of thing?
Yeah, I don't think it is. I think it's probably more related to some sort of chemical issue.
Okay.
But,
I can only imagine that it looks about the colour of betadine. So.
Yeah, I was thinking that as well, but then it should be a bit uneven because you're not going to, unless you're dunking it totally in the betadine, you'd expect it to be sort of a bit uneven in appearance. Does it look fairly even when it is coloured?
Even, but then it slowly sort of gradients off as you go down the actual cable. But yeah, it's pretty even when you look at an individual point. But I mean, maybe it is years worth of betadine. Yeah. So, you know,
could
maybe
be some solution that they're dunking it in that way. It's more in a distal part of the cord rather than the proximal part of the cord.
Yeah, the main reason I wanted to show it was I kind of thought someone might go, oh, that's the same color as some sterilization solution we use or something like that. And I thought, you know, it's just such a common one we see. So it'd be nice to sort of get to the bottom of. Another thing is, I don't know if you guys tend to use these sorts of probes with those nice ergonomic sort of handles with the wraparound silicone on them. But it's really common they start peeling off, as you can sort of see there. Again, repairable and yeah, worth dealing with because, again, they just get scummy and gel and horribleness underneath them. Moving on here, this is sort of start back into the more common things. So you can see let's see if I can line that up with some good lighting. The cable is broken at the back of the strain relief. And what's almost certainly happened there is somebody has cleaned this strain relief with alcohol, which has made it rock hard. And then the only bending is happening right at this point at the end of the strain relief. And so the cable breaks and the sheath ends up pulling back. So, but it's also common to see breaks like this, even when the strain relief is quite soft. It's just a common place for them to break.
Actually, I just had a question there.
Yeah.
I think it's back like, I don't know, maybe 5 years ago. We were really encouraged, like Transesophageal was the method of choice to clean your probes. And so then I was quite surprised to say that, you know, no, the alcohol dries everything out and is bad. Is that because the components that make the probes up have changed in recent times and are not suitable for alcohol, or has alcohol always been bad?
Alcohol's always been bad. There's been a few products come out over the years. There was one that was just called ultrasound cleaning solution or something in a little spray bottle, and it was literally isopropanol in a spray bottle, labeled ultrasound cleaning solution.
Yeah, I remember that.
I bought a box of 12 of them, and I reckon they're probably, I don't know, 7 or 8 years old now, and I'm still going through them. It's great for hand sanitizer at the moment.
Yeah. Well, we had a particular local clinic over here buy them and start using them, and they just did this run where all their probes were falling apart. I felt so sorry for them. We were able to fix a large portion of it for them, but they weren't doing anything wrong. They were just using this ultrasound cleaning solution, and it just wrecked their probes. It was terrible. Wow. So definitely don't do it. If it says it's alcohol or isopropanol, don't use it. So I don't care what anyone says. So another common one that you see all of the time is wheels of the machine scuffing the cables. And it's so manageable, just make sure that your cables are hooked up on the hooks. Obviously things do fall down and people are busy, but it's just such a shame when they get all scuffed through just from the wheels. But it's also worth checking your probes and just seeing if that's the case and dealing with it if it is.
Gosh.
It's amazing that it's taken the manufacturers this long, particularly for point of care, where the machines are moving around more, to realize that having the transducers plugged in on the lowest point of the machine often is not a great idea.
Yeah, it's kind of awkward, isn't it?
And sometimes it's just like, well, logically, why didn't you have the transducers plugging the machine up 3/4 of the way up the machine before, Yeah,
it makes so much more sense, doesn't it? I mean, obviously
sorry.
I was
going to say, but you're also getting now, if you're lucky to have enough money and you've got a fancy new ED, the machines are getting fixed in gantries over the bed, so they're not going to have that issue because they don't need to wheel the machines around so much.
Yeah, I mean, that's a nice solution, and you've got wireless probes coming out now as well. That's probably a good point to mention, wireless probes, because everyone goes, oh, that's great, they won't get damaged, but they come with their own set of problems, because if you do drop it, there's no cable to grab before it hits the ground. And the other thing is, of course, people put it in their pocket and walk off.
Yeah, exactly.
Playing with them. So
or the linen basket.
Yeah, exactly. There's all sorts of things can happen with those. So yeah, it's just one of those. There's different problems with different ways of doing it, I guess.
I love that one sticky tape together. Bit of duct tape or something.
Yeah, that'll actually be us. We would have had it open.
I'm assuming that the wireless ones would have to be charged up, wouldn't they, separately? So
yeah.
So obviously you could be scanning and the thing goes dead on you, which isn't going to hopefully happen with a cord one.
Yeah, I mean, they do have that problem. The battery life on them is normally quite spectacular, like it's something like 8 or 9 hours. And they normally charge just by being in their probe holder on the machine. So you'd actually have to be doing 8 or 9 hours of full-time scanning, which most people aren't going to go down. And they charge fast as well. Like you can pop the probe in and, 15 minutes later or something, it's charged. So they're reasonably well set up, but yeah, I guess they're expensive and, there's all those issues as well. So
have you seen the Acoustic, what's that one?
Clarius.
What's it called? Clarius one, the point of care ones that are wireless, handheld, quite bulky in the hand.
Yes.
I'm assuming that because they're point of care, they probably only last an hour or so before they go flat. Would that be correct, Sue-Ann?
I'm not sure. They've got more streamlined ones now, but it depends on how many modes you have running. Choose the battery, like all of the probes. The more things you make it do at once, the more energy it uses.
The other thing as well, a lot of the new wireless probes are coming out with, like the silicon chip-based crystals on them instead of being the actual old piezo's, and they draw a lot less power. So that's how they're getting the battery life right up with a lot of those.
Would that make them less susceptible to drop out of your sound waves if they're dropped onto the probe face?
I think it's going to be. I don't have enough data on that to really make an absolute assessment, but I can say I reckon they're going to be about the same because they're still, a very fragile, silicon based. I think they make them in like a MEMS process, and so they're going to be fragile. I think the issues they've got with them at the moment, they draw less power. The frequency range on the crystals is much, much better. So what that means is you can have a probe that does full body, basically anywhere you want to put it. You've got the great frequency ranges, so you can do whatever you want with it.
Yeah.
I think someone told me that the images aren't anywhere near as good as piezo, and I don't know why that is, but I think that's something that's currently being dealt with.
Yeah.
So, yeah, so...
well, the 3D one you had before, that's cool. Not that point of care uses 3D, but it's cool. It kind of reminds me of the old, way back in the dark ages of ultrasound, where you had the, oh God, what were they called? And you actually, is it an annular array and it just moved backwards and forwards?
Oh, yeah.
Yeah.
You want to think about that one next?
Probes. Yeah, the 3D probes remind me of how they used to operate, really.
Yes, it's not going fast anymore. It does this sort of cycle it goes through. I'll talk about the other one first, and hopefully this one will go back into a fast mode. So this is a transvaginal. Actually, Alan, can you just close that box? I think the white background might show better. Yeah, I think so. Oh, there we go. Look at that. So this is a transvaginal 3D probe. And so you can see the little ball in the top is able to swivel backwards and forwards to give you your 3D. And this is a very current probe. Like, this is how they do it. There are some that don't move the array, but it's very common still to be moving the array like that. So all the drive motor and everything is down in the handle here, and they run it up with these little drive wires and move this on the top. And then on the top is a little cap that goes over. And so if you drop that probe, that cap will bend in and smash that pivot ball section. And so it just smashes the pivots off, smashes the array out, the whole thing falls apart. So, sorry, excuse my cough. That's why it's really important not to drop 3D probes, because they are mechanical and they're delicate. Any probe really, but particularly 3Ds.
So I was always thinking, I'm always like heart in my mouth. It's a trained thing, heart in my mouth, anytime I drop a probe on the transducer end. But I'm looking at the insides of the cable connector and thinking, I've always not been as worried if I drop the cable end, but I'm looking at those insides. Like, is it as risky to drop the cable end as the transducer end?
I would say don't drop either, is the best option. You would never have dropped anything on a transducer, would you, Sue?
Oh, never. No, but I've always worried much more about the transducer end than the cable end. And then I've seen the inside of that and gone, oh my goodness, look at how much micro parts are in there.
I would say there's much less risk if you drop the cable, the connector end. Although there's lots of parts in there, they're all just electronics. And, in terms of receiving a shock, they're not going to be anywhere near as upset as it is at the actual probe end.
I think I'm going to be heart in the mouth any end right now, but anyway.
Yeah, that's right. I wish this thing would hurry up. I don't know if you can actually see that is moving. It's not quite as nice as it was before.
Wow. It was a mechanical array. Is that the right? I'm just searching the old memory banks. To create the image, they used to manually drive it so that they just
point it backwards and forwards. So this is a RAB 448. Yeah, it's a RAB 48, which is probably the most common probe out there used by baby scanning people at the moment.
Yeah.
And so it's just a shame that the machine's gone into a different mode. It's moving backwards and forwards, but much slower at the moment. But it will go faster, and if it does, I'll jump back to this to show you. But you can see this normally has a cap that sits over it like that. Same story. It's actually, I don't know if you can see this, but it's very soft if I push my finger on the back.
Yeah.
Right. So normally it doesn't feel that soft because it's full of oil, and the pressure of the oil helps to sort of stop you feeling that. But that is then right up against that array. So if you drop that, you're just going to smack right into the array, and the armature and everything that's got to move there is just going to break.
Has that been cut, or is that split?
I don't actually know what's caused that one. That is the only one I've ever seen do that, and it came from overseas. So if I had to guess, I'd say somebody else has probably tried to fix it and used the wrong oil, would be my best guess.
Oh, gosh.
Yeah. Probably the next thing to show you is, I'm sure maybe you don't do a lot of TE probes, but you're ultrasound, so let's all get exposed. So a transesophageal probe, which I'm sure you've seen, So that'd be the side you used to see. So around here, I've pulled it apart and you can start to see, there's a fair bit of electronics in that control handle. There's all the element wires that go straight down.
Fine.
When you, I won't unplug that yet. Let me just go around to here. Is that still spinning? Hang on, sorry, just give me a second. That stopped spinning. Oh, let me just start the test again. Stop. Oh, here we go. It's sorting itself out. Sorry about this. All right. So this is the tiny little tip, which you're not going to be able to see very much through a phone, right? So I've got it sitting under the microscope, and then I've got the microscope feed up here. Right. Yeah. So, whoopsies, someone who's bumping it. No. So you can actually, well, when it goes again.
It looks like the back of a watch or something.
Yeah. Things stopped working again. Hang on a second. Let me just hit start. Just make sure you didn't bomb that probe. Let me think. Yeah, it's very much like a Swiss watch in the back. There's lots of little gears and little tiny limit switches, and it's quite good technology. I don't know why.
That round black dot, is that the crystals there?
Let me sort of explain what you're looking at there. So let me flip that round. Right. So there is the front. It's a bit out of focus, but that's the front face of the probe. So when we look at it here, you can probably see that's the front face. That red bit is the array, right? And when you use the steering controls on the probe, that array spins around to allow you to change the plane that you're looking at, right? So if I now spin that back around, in order to do that, what they have is, you can probably see this spiral that comes in here and wraps around. That's a flex circuit, which is all of the element wires coming into this central pillar, and that goes down to the array that sits underneath. And then this geared cog around the outside is what actually allows the whole thing to spin. And bear in mind that the end of that, much, much bigger than the screen we're looking at here is only 10 millimeters. So they're really, really, really tiny. So it's the first time I show people that, like, who work in hospitals and are working sterilizing these sorts of probes, they get a whole lot more respect for it, because they realize there's a lot of little tiny bits in the end of these. And the biggest things that damage the transesophageal probes are things like metal sinks, because you give it a good clean and a wash in a metal sink, you only need to let go of that tip and it's smacked into the side, and the impulses are huge and it just damages the parts inside.
Wow.
So the other thing I wanted to show you is most TE probes now are going away from that mechanical design and going for more of this. So this is the GE6VT, which has, how many elements in this? 4,800 elements in the tip. So it's a matrix array. So this can do the full 3D imaging of the heart from inside. And so you can see that gets you away from needing to have that spinning array, because you can just steer it all electronically. And in the end of that is some very, very tiny wires. So if it ends up getting water in it, you've got to get it basically sorted right away. Otherwise, it's going to corrode those wires and then it's throwaway. So it's just nice to see. That probe's still not going fast. The other one I wanted to show you, this is a Philips probe, an X51. So this is their 3D cardiac probe. And although it's a little bit different to this moving array baby probe, it's sort of the next generation of technology, if you like, because again, we can do full 3D pictures without needing to move arrays around. It's all just done electronically. And this has, I think it's about 2,500 elements or something like that in the tip. Yeah, that's quite nice. And I guess the last sort of thing I thought I'd show you, which is probably pretty obvious to everyone involved, but maybe not, is just looking at this here, right? So hopefully you can see this ring down image, and it's the simplest way of looking for probe faults. It's definitely not definitive, but when you have your image of your ring down, make sure there's no gel or anything on the probe. just unfreeze it. Yeah, make sure there's no gel or anything sitting on the probe. You can look along there and you can clearly see the dropout, right? Now, if you've got big dark lines like that, you really need to get the probe acoustically tested. And the amount of times we go out to clinics and there's massive dropout regions and no one's dealt with it. So it's sort of, I think, you know, people just need to be a little bit mindful and start looking for that. Now, you can see that, what that looks like. You can see there's a fair bit out there. If we actually look at the acoustic test, there is a lot of elements out in that probe, right? So in terms of imaging, to give you some idea of what we consider to be a pass and fail, we consider no more than 3 dead elements and no 2 of those elements to be adjacent with each other is our pass criteria, which is pretty much standard across the globe. And you can see, I mean, that's got, you know, probably 20 times that out in that section. So that probe is just going to have a massive shadow in that region that's going to make it so hard to scan. There's just no point fighting your probes. You might as well get it sorted and get nice pictures. The only thing I will add to that as well is that's on your general imaging probes. So a convex probe, a linear probe, that's all fine. If you're looking at phased array probes, you can have half the array out and the image will look perfect. And it only becomes a problem when you start doing Doppler studies of pretty much any Doppler study. It will drastically affect your results. So don't get fooled by phased array probes and think, I can't see any dropout, because there still could be. And those really need to be acoustically tested.
One thing I've noticed over the years with the point of care machines, particularly if you're in a lucky situation of having more probes than you have connections to the machine, which isn't that often, is if you are disconnecting probes and putting other probes on and doing that multiple times, I've noticed quite a few times when you get dropout, sometimes it's just dust on the connector. Yes. And so first thing I do if I get dropout, which I hadn't seen before, is I disconnect it, I blow a few times on it and then reconnect it. And often I find it's dust. I don't know if you've noticed that.
Yeah, that is a huge thing. There's actually, I got called out to a local clinic a little while ago where they, it was one of these, one of these GE pinless connectors where you can't actually see inside. And they were saying that there was some dropout there and you know, the probe wasn't behaving right. And when I got down there, I was actually able to open this up and have a look inside, and there was a squashed cockroach.
Right.
So it's quite amazing the things that work their way into connectors. But yeah, definitely getting any dust or any contamination in there at all is going to give you a bad day. I just got a correction. I said this probe had 4,800. There's actually 2,300 elements. I got that wrong. So just a correction.
Still a lot.
Yeah. Oh, here we go.
How many is in a standard point of care probe, for example, like a standard linear, for example?
Probably anywhere between 128 to 256, something like that.
Wow.
So this probe is now running. So you can see that mechanism driving that probe backwards and forwards. And obviously when the machine does it, it does it a lot faster than that. But that's basically what happens when they're scanning for 3D babies.
Wow.
And the last thing I thought I'd just show you is I've mentioned many times about acoustic testing, but I haven't sort of gone into depth as to what that is. So this is our acoustic tester here. We're able to plug probes in. Every probe needs an adapter, and we have suites of adapters that we can use to connect the machine. Probe gets put in a water bath in a target. So you can see that probe is actually facing down there at a target at the bottom. So we then fire each one of the crystals independently, and we look for the reflection. And particularly interested in, I mean, it measures lots of parameters, but if we go measure there, you can see the sensitivity plot that's coming up. And you can see this probe's got lots of problems, but we can straight away see what elements are performing and which ones aren't. I think on this probe, let's just see if it does it. Just this bit that's coming up. You see this nice curve down backwards and forwards. that will either be a lens delamination just from the shape, or there's a bubble sitting on the probe face that I haven't cleared off properly. And so it's quite nice for doing all sorts of diagnosis. And there's the capacitance of each element. So lining up the capacitance and sensitivity, we can then, this is probably hard to read, but we can basically do fault finding of what that fault is, whether one goes down and the other one does, or whether it's just one and not the other. So hopefully that's given some useful information.
It's like I said, I have always worried about the transducer end. I think I'm going to worry about the connector end a little bit more too. But it's fascinating to see. I don't know that I've ever, like, I've seen the strain relief go quite commonly, but some of those other ones are quite spectacular. And I'm sure it's just run of the mill for you. But yeah, it's important to keep your probes nice so that we're being safe for our patients.
I mean, yeah, safe for your patients. And also, I think if your probes have got a whole bunch of elements down, you're just making your life hard. It's going to take longer to get the scans that you need, and time is money. So you're better off just getting it sorted.
Yes.
I know you're not a manufacturer, you're a repairer, but why do you think it is that, you know, if you, like the other thing to talk about is the power cord, especially for the cart machines. Why do you think it is that they haven't moved more to like retractable cords, like in a vacuum cleaner, or more docking stations where you have a permanent power source and you move the cart in there? Why is it this sort of like cord that you've got to plug in, and you might forget to turn it on, turn it off. You might forget to pull it out before you move the thing. What do you reckon is the rationale for why they've not changed to these things in a small way?
Having an option where you sort of put it in a docking station, like you mentioned, makes a lot of sense. I mean, even the vacuum cleaner idea, it's not a bad idea. It doesn't make sense probably for, you know, general ultrasound, but certainly when you start talking in emergency and places like that, I mean, it's perfect, wouldn't it?
Do you know those cords are often the same that sort of just plug into a kettle? We took some machines over to, they were Australian compatibility for electricity, but we took them over to Brunei, and of course plugging them into the Brunei Australian electricity converter didn't work so well. So we just went to the local electronics store with a translator and got a new tea kettle cord and plugged it in, and it worked fine. But I was just staggered at it's a simple tea kettle cord.
Yeah, well, it's an IEC connector, International Electrical something or other. It's a standard international connector that's used on computers and kettles and everything, and that's why they use that, because it's compatible across the board.
Yeah. I like the idea of a retractable cord, Alan. You'll have to get yourself onto some advisory committee.
No, that's already in the works, I've heard, and docking stations are in the works. I just sort of wonder why it's taken people that long to realize that, you know, because people run over the cords and pull out the cords accidentally and do damage on the power cord end as well. And sure, it's not that expensive usually to fix most of the time, but it's still a hassle every time you've got to go and get a new cord.
Yeah. It's the same on most medical equipment, though, isn't it? Like even like infusion pumps and things like that, they're typically just an IEC cable, which is weird.
Yeah. They're probably more robust than some of the cables that we can get, I guess.
Yeah, I suppose at least they're more robust than if you run over the transducer cable. They tend to last a bit longer.
Yeah.
Well, thank you so much, Ashley. I found that fascinating. It's, I mean, it's something that I hold every single day pretty much, and you kind of just use it and don't pay too much attention, really. It just works or it doesn't. But seeing what the insides are doing and how much wizardry is on the inside of these pros is fascinating.
Now we know why they're so expensive. Yeah, once you look at the inside of them, you realise.
I wouldn't want to be the guy who has to collect all those fine wire to, it's probably a robot, but even so,
it's not by hand. We actually do that. So if we're replacing cables, we'll solder the ends of them. And to make it worse, those little tiny cables, they're not just cables, they're actually coax. So they have an outer sheath and an inner core.
Wow.
So that probe there has had its cable. Oh, hang on, I've got to flip my camera. That probe there, which I'm still not getting the right.
On a lighter note, is any of it gold? So if it's broken, can you just melt it down and get rich? Because isn't gold like one of the best conductors?
Yeah. Yeah, so this probe has had its cable replaced. We've just finished that job. It's for a customer. And yeah, each end needs soldering.
Yeah, wow.
So yeah, it's a big job.
Wow. Well, thank you so much, Ashley. That's it's fascinating. I love it. And I guess for any of you who want to ask some questions that are going to be offline, now's your opportunity. But once again, thank you to Philips for supporting the Coaching Corner tonight. And I'm keen to hear if any of you have any ideas for next month.